All right, good afternoon, good morning, good evening, depending on where you're at today. Today we'll continue our talk into chapter 7, and then we'll move into a little bit of chapter 8, which is hypothesis testing. Okay, so just last time, I just want to review. Today's goals is we'll get into hypothesis testing. So it's another method of statistical inference. So at this point we have, confidence intervals, which are used to make decisions based off data. And now we have hypothesis testing, which can also be used to make decisions based off data. So in this example here, what we want to do in today's lesson, we're pretty much going to generalize the steps for hypothesis testing and include the 4 steps for hypothesis testing in dealing with the sample proportion or population proportion. So this quantity that we'll see here, this is what we call, it's really just a z-score, right? The value we use to find probabilities underneath the normal curve. But this here is, of course, we're going to call it a z-test statistic. But just from last time, we were comparing 2 population proportions with confidence, and there's just some extra things I wanted to add. And so just to note that, we want to know from population 1, from population 2, we take a sample out, and what we want to know is usually, are the proportions equal or not. And one thing to note is that the population proportions for population 1 and 2 could be the same. But it's pretty much guaranteed that when we take a sample proportion from each population, that they're guaranteed to be different, due to randomness and variation of our study. And so we want to know usually whether or not they have the same proportion, or whether or not there's an extra difference or not. So as far as the formula goes for a confidence interval for in studying 2 populations, we're just saying that while we're examining the difference in proportions, so our estimate for that is the difference in sample proportions. Okay, so the sample proportions is what we'll use to estimate the true difference in proportions. Okay, so we say this is like our point estimate for it, and now we're going to add a margin of error. So we're going to do plus and minus this margin of error here. So what's underneath the radical sign, that is the standard error for the difference in proportions, and the z star is just pretty much telling us how many standard errors do you want to include in the margin of error, right? And so how we find the z star is the same method that we use in one sample proportion. So just as far as notation goes, it's very important you keep track of how you label the notation here. But here p hat 1 is sample proportion from population 1, Edinson 1 is sample size taken from population 1, and here we have the sample proportion and sample again, but from population 2. So these numbers do not need to be the same, but it's very important that when you take this difference here, you know which is 1 and which is 2. Okay, so just as far as checking conditions, we need them to be random and independent. We need large samples. That means within each sample we have at least 10 successes and 10 failures, and we need big populations. So we're just saying that the population, each population, that their sample size, that the population is at least 10 times larger than the sample sizes. Then of course here between the populations we need the responses to be independent from each other. Okay, so in this example what we did is we asked on college campus, we're asking whether or not is there a difference in opinion and whether college was worth it between genders here. So we say, is college worth it? In the table below we wish to see if there is a difference between genders. Okay, so here we see out of female, 582 out of 629 said yes, college was worth it. For male, we have 403 out of 460 saying yes, college was worth it. So it seems overall that, good for us that the majority thought college was worth it, which is great. Okay, but what we want to know is there a difference between these 2 groups here, right? So this comes from a sample of data, so a sample of 1,089 students. So we assume that how they collected the sample, it was a random sample. We assume the responses from each participant, they're independent from each other, and we assume that the population size of the campus is at least 10 times larger than this number here, right? Actually, than this number here. So If we do 10 times larger, well, we just multiply it by 10. So really, our population size needs to be at least 10,890, right? So, so I think that's safe, at least for our campus, right? And so, and of course, here we have at least 10 failures and 10 successes, at least 10 failures and at least 10 successes for this here. So remember, successes here, that's just what we're counting. So we're counting the number of yes out of the total number, right? So whatever we're not counting, we call it failure. But either way, we have more than 10 for every category. So therefore, using this confidence interval is justified. Okay, so here we have, so here we go ahead and construct a 95% confidence interval for the difference in opinion. So here I have the proportion of the female minus the sample proportion of male. Okay, and I'm doing 95%. So here we want to include a margin of error of, we want to include 2 standard errors. All right, so sometimes you put 2, other times you may see 1.96 here. And then here, this is just the standard error for the difference in the proportions. Okay, so just make sure you keep track of your numbers. Make sure that this sample size of sample 1 sticks with the sample proportion of sample 1. Try not to mix those up as you work this out. Okay, so what we concluded here is that 1.2 to 8.64% difference in opinion. So right away, because all of these values are greater than 0, right, we can conclude that female college students are more likely to admit their college was worth it in comparison to male. Okay, so really with these types of intervals, we want to know, is 0 included in our interval? So so we ask ourselves, is 0 included in the interval? If so, we can't rule out the possibility that population proportions are equal. Okay, so meaning if this value here were say negative 1.2% to 8.64%, 0 would therefore be in our interval. And any value in our interval is plausible. Okay, it's possible. So therefore we wouldn't be able to conclude that there's a difference in the proportion of opinions for these students here. Okay, so, and of course, and it doesn't always have to be 0, especially when we're studying, differences in opinion between Democrat and Republicans. Maybe we already know there's a significant difference between the two parties, but we want to know if it's increased over the past few years. So, this 0 we can replace with, 5%, right? We already know there's a 5% difference. We want to know whether it's included or not. But pretty much what this is telling us is, but most of the time, we just want to know if there's a difference or not. So we're looking for whether there's zeros in our interval. And so in this case, what we got here is that they're all positive values. So they're all greater than 0. So we're just saying, what does a positive value mean? Well, it means we have to know which population was assigned to population 1 and which was assigned to population 2, right? Because we're doing population 1 minus population 2. So I did proportion of female minus proportion of male. So the only way that difference is positive if proportion of female is greater. So that's why here I know right away that this is saying, okay, well, the females are more likely to state that college was worth it. Anywhere between 1.2% more likely or 8.6.4%. Okay, if these values were negative, okay, if I had negative 8.64 to negative 1.2%, well, then we're saying that the males are more likely to say that college was worth it. Okay, so, and one other thing that we want to add is, in other examples, usually we talk about random sample, okay, but we could have random assignment of a random sample. So that just means that if the two samples are not random samples, but instead objects are randomly assigned to groups, right? So remember in the controlled experiment, we have a random sample and then we flip a coin and we say, okay, you go to treatment, flip a coin, you go to treatment, flip a coin, you go to control. So we randomly assign them into the various groups, right? So that's what they mean there, that we can apply this methods within a controlled experiment to see a difference between two populations, meaning mainly the treatment group and the control group. Okay, so that's all I had to say very briefly about this brief example, just to give a brief rundown, but mainly just to give a heads up on how we interpret these intervals. And usually we're looking for 0 in the interval, whether it's in there or not, when we're examining the difference in proportions. Okay, but next time we come back, we'll get into hypothesis testing.